Welcome to this edition of Models to Ace. Presenting an Excel spreadsheet-based model to derive the solution to an assignment problem under given preconditions and constraints. Using linear programming, we will design the model for deriving the sequence of coaches for a mock drill for a presidential convoy, along with the assignment of Secret Service representatives in the coaches. The convoy consists of a sequence of 7 coaches. The slots in the sequence, starting from the first, are numbered 1 through 7, respectively. The 7 coaches are designated: Ambulance, Roadrunner, Overwatch, the Hosmet, the Hawkeye Renegade, the ID car and the Watchtower. The order of the coach names has no relation whatsoever with the order they would occupy after they are assigned to the respective slots in the convoy sequence. Obviously, only one coach can be assigned to a slot. There are 7 Secret Service representatives or SSRs, popularly called agents. They are designated code names: Growler, Mayor, Aston, Blue Star, Amazon, Striker, and Roller. The problem involves the task of sequencing the 7 coaches into the 7 slots in the convoy. For a primer on this problem and a solution to a more complex sequencing scenario, please refer to the video titled Linear Programming Model, Optimum Assignment Sequencing. The sequence is subject to the following constraints. The ambulance cannot be assigned to the last slot in the convoy. The Hosmet must be the leading vehicle in the convoy. The coach Hawkeye cannot be placed beyond the 6th slot in the convoy, and the SSR Striker must be deployed to it. The SSR Blue Star must be deployed to the coach, the ID car. Overwatch cannot be placed in the 2nd or the 6th slots, and the SSR Growler must be deployed to it. The Roadrunner must be assigned to the 4th slot in the sequence, and the SSR Amazon must not be deployed on it. The SSR Roller must be deployed to the Watchtower. Every SSR must be deployed to a coach, and every coach must have only one SSR deployed to it. We now set up the model in this spreadsheet in order to solve the sequencing problem. We do this in the tab titled Model, Convoy Sequence. Here, we formulate the assignment problem as a linear programming problem. The model derives 2 sets of assignments. In the first section, the model assigns the 7 coaches to their slots in the sequence of the convoy. This is depicted in the section labeled Sequence Coach Assignment. In the second section, the model assigns the 6 Secret Service representatives to their corresponding coaches. This is depicted in the section labeled SSR Coach Assignment. Finally, in the third section, labeled the Final Sequence, the model presents the final mapping between slots, coaches and SSRs. These assignments constitute the decision factors or controlling factors of the model. These are shaded in green in the model shown here in the spreadsheet. Since the assignment tables of the 7 coaches to their slots in the convoy, as well as mapping to SSRs, have the list of coaches as the common factor, we place this list in this purple-colored block here in the middle, under column L. So, we have the sequence coach assignment section to the left, here, in column C through I, while we have the SSR coach assignment section to the right, here, in columns M through S. The binary matrix, shaded green, in rows 4 through 10, column C through I, represents a set of decision variables for the solution sequence. This matrix contains an element corresponding to each coach sequence pair. For example, a value of 1 in cell H4 implies that the coach designated ambulance comes in the 6th slot in the sequence of the convoy. By extension, this also implies that ambulance cannot come in any other slot. To impose this condition, we create the derived column titled Total, column J, to the right of the sequence coach assignment section. For example, cell J4 contains the sum of all zeros and ones corresponding to slots assigned to the ambulance in this first row in the decision matrix. Clearly, this sum can have no value other than 1. The same is true for each of the remaining 6 coaches. Hence, column J under the heading total, must contain an array of only ones. Another obvious consequence of this assignment of ambulance to the 6th slot is that there can be one and only one such choice regarding the 6th slot, from among the 7 possible coaches. Hence, each column of the decision matrix must contain one and only one value of 1, the remaining being 0. This array along row 12, column C through I, contains the column-wise sum totals of the 1s and 0s in the respective column. For example, this cell C12 contains the sum of these 1s and 0s under column C in the decision matrix. Obviously, this sum in C12 must be equal to 1 and only 1. Hence, this array along row 12, column C through I, must contain only 1s. All of these 7 ones must add up to the grand total of 7, as shown here, in cell J12. This is the target of our linear programming algorithm. We have given a name to this cell, total sequences covered, using Excel's name manager. Let us open Solver to check how this is set in the objective function. Here, we see that next to set objective, we have supplied the name total sequences covered, which refers to the cell J12, and have stipulated that this must exactly equal a value of 7, here, in objective criteria. Note that this is a redundant objective. If each of the values in the array sequences total across coaches, C12 through I12 has a value of 1, their sum will obviously equal 7. However, we retain this objective, solely for semantic purposes. Next, this binary matrix, shaded green, in rows 4 through 10, columns M through S, represents another set of decision variables for the solution sequence. This matrix contains an element corresponding to each SSR coach pair. For example, a value of 1 in cell Q4 implies that the SSR designated Amazon is deployed in the ambulance, in the convoy. By extension, this also implies that ambulance cannot have any other SSR deployed to it. To impose this condition, we create the derived column titled Total, column T, to the right of the SSR coach assignment section. For example, cell T4 contains the sum of all 0s and 1s corresponding to SSRs deployed to the ambulance, presented in this first row in the decision matrix. Clearly, this sum can have no value other than 1. The same is true for each of the remaining 6 coaches. Hence, column T, under the heading Total, must contain an array of only 1s. Another obvious consequence of this assignment of Amazon to the ambulance is that there can be one and only one such choice regarding Amazon, to one among the 7 possible coaches. Hence, each column of the decision matrix must contain one and only one value of 1, the remaining being 0. This array along row 12, columns M through S, contains the column-wise sum totals of the 1s and 0s in the respective column. For example, this cell M12 contains the sum of these 1s and 0s under column M in the decision matrix. Obviously, this sum in M12 must be equal to 1 and only 1. Hence, this array along row 12, columns M through S, must contain only 1s. To simplify mapping and mathematical operations, we have attached integers to each of these 3 classes of categorical variables. The SSRs or agents, the coaches and the slots in the sequence of the convoy. We map an integer sequence to each of these lists, to refer to the corresponding member. For example, in this obscured column A, we maintain a list of 7 numbers from 1 through 7, referring to each of the 7 coaches, in the corresponding row. Thus, this value of 1 in row 4, refers to the ambulance. This value of 2 in cell A5 refers to the roadrunner, and so on. These values are hidden from view, by using the white font color, the same as the cell backgrounds. Using Excel's name manager, we name each of these cells to correspond to the coach, being referred to. Thus, cell A4, is named ambulance, A5 is named roadrunner, and so on. Similarly, this obscured first row, at the top, we maintain a sequence of 7 integers, from 1 through 7, referring to the 7 slots in the sequence with identical labels. Using Excel's name manager, we name each of these cells to correspond with the sequence number being referred to. Thus, cell C1 is named sequence number 1, D1 is named sequence number 2, and so on. In the same row, we maintain another sequence of 7 integers from 1 through 7, referring to the 7 SSRs. Using Excel's name manager, again, we name each of these cells to correspond to the SSR being referred to. Thus, cell M1 is named Growler, N1 is named Mayor, and so on. Again, launching Solver, we can verify that the 4 arrays of sum totals, array of totals of SSRs across coaches, array of totals of coaches across SSRs, array of totals of sequences across coaches, and array of totals of coaches across sequences, are set to be arrays of ones. Also, the values in the 2 decision matrices are constrained to be 1 or 0, by these constraint conditions. Coming to the remaining derived data sections are these 2 ranges labeled sequence hash, and SSR hash attached to the coach SSR assignment section, under column Y and Z respectively. This array attached to the coach SSR section, simply records the sequence number of the corresponding coach, as a consequence of the 1s and 0s placed in this binary matrix, by the model. For example, this value of 1 in the cell H4, indicating the assignment of ambulance to slot 6, translates to a value of 6 in the cell Y4. This can be elegantly obtained by performing the sum product operation between these 2 arrays, the binary array carrying information about the slot assigned to ambulance, and this array containing the exhaustive list of possible slots, denoted by tagged integers. Since ambulance cannot be assigned to the last, or the 7th slot in the sequence of the convoy, and since 7 is the highest value possible for a slot, we express this constraint by this inequality, less than or equal to 6, for the sequence number of the ambulance, in this gray-colored cell X4. The Roadrunner must occupy the 4th slot in the convoy, the Hazmat the 1st slot and the Hawkeye Renegade the 5th slot, as depicted by these constraint labels in these gray-colored cells here, along column X. Similarly, the model derives this array of SSRs attached to each coach in the convoy, by performing similar sum product operations, between the binary arrays carrying information on SSRs attached to coaches, and the obscured array of integers tagged to SSRs. Let's check this out by expanding this first row. Performing similar sum product operations, but along each column, corresponding to a slot in the convoy sequence, this time, the model derives this row-wise array, along row 13, labeled coach hash. It simply reproduces the coach assigned to each slot in the convoy, as a result of the choices recorded in this binary decision matrix, by the model. Similarly, we derive this array, along row 13, columns M through S, denoting the coach associated with each of the SSRs. As a corollary to the model choosing the mapping between each of the 7 coaches and its SSR, in this section, SSR coach assignment, observe that consequently, each of the 7 SSRs gets automatically associated with the slot in the sequence of the convoy. For example, as Overwatch is assigned to slot 3, and is assigned to the SSR, Growler gets associated with slot 3 and vice versa. This can be elegantly captured by a sum product between this assignment array of Growler and the coach sequence mapping array in column Y. This is captured in cell M14, here. Repeating this computation for each of the 7 SSRs, we get this binary array, along row 14, columns M through S, labeled sequence hashtag, indicating the slot in the convoy, each SSR gets assigned to. Extending this logic, to the sequence coach assignment section, we get this binary array, along row 14, column C through I, labeled SSR hash, indicating SSR that each slot gets associated to. Let us examine the names we have assigned to individual cells and ranges, in this model, to simplify formulation and interpretation of constraints in Solver. In this binary decision matrix, in the sequence coach assignment section, shaded green, each cell is named by a string formed by the name of the corresponding coach and the slot number, separated by an underscore. For example, cell C4 is named ambulance_1, and so on, all the way till the cell I10 named watchtower_7. This array of totals, along column J, is named array total_of_coach_across_sequences. This array along row 12 is named array total_of_sec_across_coaches. The array below it is named array sequence_coach_mapping, and the one below it named array SSR_sequence_mapping. The dummy objective cell J12 is named total sequences covered. Similarly, in the SSR coach assignment section, each cell in the binary decision array, shaded green, is named after the coach and ambulance it represents. Let's check out the cells along this binary decision matrix, all the way up to the last cell S10, here. This array of totals, along column T, is named array total_of_coach_across_SSRS. This array along row 12 is named array total_of_SSR_across_coaches. This array, along row 13, is named array SSR_coach_mapping, and this array, along row 14, is named array sequence_SSR_mapping. Finally, proceeding to check this last two derived arrays along columns Y and Z, we note that this array along column Y is named array coach_sequence_mapping, and this array to its right is named array coach_SSRS_mapping. Let us now examine the hard constraints for this sequencing problem. In addition to the gray-colored label cells capturing constraints that we have seen all along till now, there are comments attached to decision cells, highlighting the constraint attached to that cell. For this, we use two named values, obscured in these two cells B16 and B17, using the same font color as the cell background. Let us expose these, using a visible font color. This cell, B16, containing the value 1, is named possible, while the cell B17, below it, contains the value 0, and is named not possible. These will be used while formulating constraints in Solver. Launching Solver, let us examine the constraints. The ambulance cannot be assigned to the last slot in the convoy. This is captured in this constraint. The Hazmat must be the leading vehicle in the convoy. This is captured in this constraint. The coach Hawkeye cannot be placed beyond the 6th slot in the convoy, and the SSR striker must be deployed to it. This is captured in these two constraints. Note how the naming of the binary values of 0 and 1 as not possible and possible makes understanding these constraints easy and intuitive. The SSR blue star must be deployed to the coach, the ID card. This is captured in these two constraints. Overwatch cannot be placed in the 2nd or the 6th slots, and the SSR growler must be deployed to it. This is captured in these two constraints. The Roadrunner must be assigned to the 4th slot in the sequence, and the SSR Amazon must not be deployed on it. This is captured in these two constraints. The SSR roller must be deployed to the watchtower. This is captured in this constraint. Summarizing the details of the model, covered in the Model Convoy Sequence tab, the decision variables are the binary values in the cells shaded in green. These determine the two sets of primary assignments and mapping, the coach sequence assignments and the SSR coach assignments and other derived assignments. The objective function, a redundant one in this problem, is the total number of assignments of coaches against slots, which must be equal to 7. The functional constraints, arising due to the particular formulation we have used for the model, are that all decision variables must be binary, there must be only one association between a coach and its slot, and finally there must be only one mapping between an SSR and a coach. The constraints, specific to this problem under consideration, are the hard constraints on assignments of SSRs to their coaches and coaches to their slots. Having reviewed the decision variables, the objective function, functional constraints, and the model parameters, let us clear out the cells containing the decision variables. Observe how the final sequence table, below, loses its values and becomes populated with not applicables. We now launch Solver, select the option to make unconstrained variables non-negative and select the simplex LP method for deriving the solution. We now instruct Solver to derive the optimum solution. Solver reports that it has found a solution, where all constraints and optimality conditions are satisfied. This is the set of decision values that Solver has generated. The solution suggests these deployments of SSRs to coaches, along with the slots in the convoy, the SSRs get assigned to, as a consequence of the decisions. It provides the mapping of the coaches to the sequences in this section and consequent mapping information, in this section. Observe the mapping produced by the model, between slot numbers, coaches and SSRs, in this table. The model produces two categories of decisions, the same as the decision variables. These are the decisions of assignment of coaches to slots in the convoy and assignment of SSR to coaches. As a consequence of these decisions by the model, a group of attendant associations gets formed immediately. These are the associations between an SSR and his slot in the convoy. The final mapping is automatically reproduced, in a compact manner for easy visualization, in this table, below. The sequence numbers are manually generated in this first column of the table. Data in all the other two columns is computed from the decision and consequent using Excel's VLOOKUP and LOOKUP functions. For this, we construct three name tables for converting tagged integers to their corresponding names. Before examining these tables, we need to expand this first column, this first row, and make the integer tags visible by changing the font colors to a visible color. Launching Excel's Name Manager, let us scroll down to these three tables, name tab_coach, tab_SSR, and tab_sec_coach_SSR_ mapping. Let us examine the name table tab_coach. It is a vertical table extending from these integer tags for the coach names to the coach names in this last column. Closing this, and launching the edit dialog box for tab_SSR, we observe that, this time, it is a horizontal table extending from integer tags for the SSR names, to the SSR names in this last row. Launching the last table, table sec_coach_SSR_ mapping, we note that it is a horizontal table, with the slot numbers in the first row and integer tags corresponding to SSRs in the last column. We use lookup and VLOOKUP functions on these tables to convert integer tags into the names of coaches and SSRs. For example, in this cell D18, we first match the slot number of 1 in cell C18, in the first row of this horizontal table of sequence numbers, named array tab_sec_coach_SSR_ mapping, in this range of cells from C1 through I14. On row 14 we get the coach number, mapped to that sequence number, from this 13th row. We then look up the obtained coach number, in the first column of this vertical table, extending from column A through L, to fetch the coach name corresponding to the coach number. A similar logic is replicated for determining the SSR in this third column. These formulae used in the first row, are replicated to the remaining 6 rows, simply by dragging the selection of the first row, over the remaining rows. Thank you for giving Models to ACE the opportunity to serve you with our analytical models. Please subscribe to our channel for more.